Welcome everybody to this year's sambaXP. Greetings from Miedebach in the middle of nowhere in Germany on a fine evening. I'll try not to waste too much time with the introduction stuff here and start sharing my screen. Oh. Asking me some questions. Okay, I'm allowing it to share screen. You're sharing the screen. Okay, it's telling me I'm sharing the screen. I now switch to my slides. Can you see those?
Yes, we can see.
Okay, okay. Now let's try slideshow mode. Didn't work the last time I tried in our internal testing. Does it work now?
Yeah, we see it.
Okay, okay. So hey, so there are so many participants in this presentation. So I really guess most of you should probably either get some sleep or maybe get a beer. This is the developer's guide to SMBD presentation. This is aimed at, yeah, I'd say beginning SMBD file server developers. So I guess folk like Jeremy, Volker, Metzer, you should get dinner and maybe a beer or something like that. And everybody who's not really interested in working on the SMBD file server code in Samba probably might want to do that as well. But you are free to join this presentation. But be warned, you might fall asleep. So yes, so this presentation is about giving a kind of overview, reference, and introduction into our file server. I start with an overview. I'll do a quick overview of the most important libraries and subsystems we use in the file server. Then, hoping time permits to finish all of this, I'll start with a deep dive into the SMBD file server sources, starting with the main function and actually going down into processing of SMB2 create requests and how we go all the way down in our stack and process that. In some kind of overview to give an introduction to what is happening there under the covers. In the end, there is a small reference section which I'll kind of skip in this presentation. It's just kind of a small reference for future readers of the slides to have an overview of the main components in the source tree. There are some links and there'll be some Q&A in the end, maybe if time allows, which I'm a bit skeptical because I have a lot to cover. So let's start with the file server overview. Our SMB file server. So yeah, it starts with processes. So in SMB, the file server, you probably already ran across that. We have the SMBD process, and actually not only one, but depending on connections, a bunch of them. So there's a parent SMBD process which creates child process. So we have forking architecture. We have a parent SMBD process which sits there listening for SMB connections on port 445. And when a client comes in, the parent accepts the TCP connection, calls the fork syscall, and which creates the child process. And from then on, the child handles the connection and the parent just moves on, again, accepting new connections in case any additional connection comes in. So the real magic happens in the child. So in the child, trying to separate this in some kind of logical subsystems, we have our SMB front end, so how I would call that, which does the network I/O and the SMB packet processing. Then we have a very large lump of code, which actually implements the Windows NTFS file system semantics on top of POSIX file system or whatever we have underneath Samba. More on that later. And we have our so-called VFS, virtual file system abstraction, which abstracts away the file system access we do. And then there's actually more. SMBD is not just a file server. It's also a database for user accounts and groups in a Windows fashion, so-called SAM, the Security Account Manager. So you have users and groups in a full Windows fashion, including passwords, group memberships, which supports all Windows semantics, and is also actually providing an RPC server in the SMBD process. So Windows uses RPC a lot, so you can query this user database over RPC. All this is part of the SMBD process. So a few more words on why do we fork. So we have one SMBD process per connection, and this provides security. So we let the operating system do all the permission checking by switching user ID and group IDs. So we impersonate the Unix account for the user to leverage the operating system permission checks by the kernel. This provides reliability because, yeah, if you are unlucky and your process crashes, other users are unaffected by this. So this is, yeah, bad for you, but good for the others. If you have a single process model, that process crashes, then of course, yeah, what can you do? You're screwed. This also nicely provides scalability. In the SMB file server, we have a lot of sync processing, which gets nicely parallelized. Oh, too many else, so it's too late in the evening, by having one process per connection. Here's a overview of how that looks like. I mean, it's basically simple to picture if there you have a parent process and child processes. But this overview contains more. And what I'm trying to show here in this picture and this overview is that so in each child you're handling an SMB connection or an SMB over TCP connection. So this is actually only true without multi-channel. With multi-channel, you could actually have even more than one TCP connection per process in the child. And now for SMB2, you can have multiple authenticated sessions actually for different users in one process. And the tree connects, the share connects of the users are hanging off the sessions. They are tied to the sessions. And what I'm trying to show here is that for SMB1, this is a bit different. The multiplexing for SMB1 is done differently. You can see here you can also have different sessions in this process on one TCP connection. But the tree connects are not hanging off the sessions. They are hanging off, yeah, well, not actually the connection. Well, oh yeah, so they're in the process in the child, and the sessions are multiplexed across the connection. SMB1 request contains a tree connect ID and a session ID. So this is done different, and this can be confusing when you start looking at the code. So on we go. So we don't only have SMBD, we also have this strange thing called WinBind. What is that? So WinBind is a process, of course. Actually, there are also then a bunch of them when you start it. And this is typically important when you join a file server to a Windows domain, for example. Previously, in earlier Samba versions, you didn't really have to run WinBind, but these days it's kind of mandatory to run WinBind, especially if you're running in if you're joined in a domain. So what does WinBind provide? So one thing is it sits there as an NS switch module and allows users and groups from Windows domains appear as local operating system users and groups. Then it's kind of a domain authentication proxy. So SMBD forwards authentication requests to WinBind, which is true for NTLN authentication, not so much for Kerberos. Some magic happens there as well, where SMBD talks to WinBind, but For NTLM authentication, it's Winbind that talks to domain controllers, and SMBD just talks to Winbind for that. So Winbind here as domain authentication proxy. Winbind then is a kind of central store and instance that does identifier mapping. So in Windows, you have SIDs, and POSIX, we have IDs. So IDs, user IDs and group IDs. This is called ID mapping. And this is done in the Winbind process. That's one part of identifier mapping. We also do SID to name translations. This is an RPC service where we actually talk to domain controllers. And all this is done by Winbind, and basically whenever SMBD has to do any sort of this business, it talks to Winbind. Winbind caches this stuff, so it will only talk to domain controllers if something is not in the cache, so which is actually quite nice. So yeah, so now I want to give a brief overview of what happens after authentication has successfully taken place with Kerberos or NTLM as authentication mechanisms, because the thing is, and the SMBD child process that runs the connection for the user, as said before, it wants to impersonate the Unix account for this user. So we need the Unix account. We need a name for the Unix account. We probably need at least a home directory for the user, because that might be in the SMB, in the Samba configuration, might be set up to share a home directory. And of course, we need the user IDs and group IDs to impersonate the user at the Unix level. So what do we get from the authentication process after successful authentication? We get the names of the domain and the username. And yeah, we get Windows SIDs, the user SID and auxiliary group SIDs. And we typically get those from the so-called pack via NTLM or Kerberos. So what do we do with those? Yeah, we need to form a Unix account. So this is a very nice overview, I think, of what's happening behind the scenes. At least parts of it. It's not complete. But it gives an introduction, maybe that serves as a starting point to give you an idea of what's happening. And the first thing that happens is that the SMBD process uses the libc get pvnum library call to get the user account struct password from the name. And via an S-switch, supposedly that Winbind is configured, and an S-switch as a module. This goes to Winbind. Winbind does some internal processing here, starts at some internal machinery. The first thing it has to do, it gets the name. So it has to ask a domain controller to, from the name we got, get the SID back. Once we got the SID, we get back there. The next step is we translate the user SID to user ID. This goes into the ID mapping subsystem in Winbind. ID mapping is part of Winbind, and this is configurable, so you can have different ID mapping backends. There's an algorithmic mapping backend that's called ID map RIT. There's another one, ID map _ ID, which uses RFC 2307 to query LDAP servers. In this case, yeah, domain controller. This is probably supposed to be a Windows Active Directory domain controller, which you can query via LDAP to get the POSIX user ID from the account. So now we got a user ID. This is one very important piece. You need to answer this question, user ID for the user. Great. So we need more. Concentrating here on impersonating the user account. So we need the user ID and we need the group IDs. The next thing to get the group IDs is SMBD now goes directly to Winbinds. It's using this function, SID to Unix IDs, which internally also, that's kind of missing here. It also does some Winbind request response to just that's the function to low-level function, which does the communication between SMBD and Winbind across the Unix domain socket. And this goes into Winbind, and then again, we basically use the same function to get the group IDs for the SIDs, right? So hopefully this gives you an idea how this very complicated process is set up and started. There's a lot more happening to get additional fields for the user, like the primary group ID and the home directory as mentioned and so forth. But this is maybe some important parts of the process to get you started. So next, let's look into more detail libraries and subsystems that we have in Winbinds, continuing on our high-level overview of the file server. So the main important libraries we have that you should get familiar with if you're starting to hack in Samba are our event handling and async processing abstraction libraries, T-event, our memory allocator, talloc. We have a database, the key value store TDB, which is typically used and consumed by the DB-rep API in the file server. We have tsocket and async socket programming library, which is quite low level, so you might not run into this very soon when you start working on the code, but you might hit it sooner or later, and it is nicely encapsulates all socket IO stuff in an async fashion, also building on the T-event abstractions on top. The sources of all of this is in the lib top level subdirectory. And the good thing is we have some very nice tutorials on talloc, T-event, and tsocket. These are all clickable links, so these links here will work anywhere. This link here will probably only work here on my system because the file URL is specific to my setup, but it's a relative path inside the Samba source code git tree. So our VFS, the abstract file system interface, as mentioned before, this is an abstract interface to how the way actually accessing low-level POSIX file system functions like read, write, or pre-read and pre-write, or open, or anything like that. That is the POSIX API for working with files. It also does a bunch of other more high-level functions. And the VFS, it provides the loadable and configurable modules that implement the whole interface or just parts of it, which is also possible. And this is a little bit much like a Fuse for the kernel. There's a VFS default module, which basically maps to the POSIX scrolls directly. And finally, as mentioned by Andreas Bokovoy earlier, you actually could do, or it seems that it had been done something like 15 years ago, probably as a funny prototype or something. You could actually write a VFS module where all file system access goes into an SQL database. Right? And there is a very nice tutorial. So I'm not going into any more detail on the on this VFS thing. If you want to learn about it, there's a good tutorial on the Samba wiki about writing Samba VFS modules, and all that stuff. All the modules are in source 3 modules. Briefly, want to mention this this subsystem here, which we use for IPC. Messaging based on Unix datagram sockets. We need that because now that we are split into multiple processes, sometimes you have to coordinate and communicate between the processes, for example, for doing least breaks and upload breaks and other stuff. It actually also supports sending messages to itself, I think, at least, should be. And this is what the API looks like: messaging send to one, a unicast message, a broadcast message. This is how listening for messages looks like. This is stuff you will run across quite quickly when you start working on the code. So spending some time learning that and understanding that might be worthwhile. And but just with this, knowing that it's there and how it's work, and maybe looking at what happens, how this is, for example, this is async processing, so it supports callbacks. So essentially, you don't have to understand how it works under the hoods, but knowing that you can send a message and then be notified when a response comes in and something there. That's how it works. So dbrep, I said before, it's an abstract database interface we have. In Samba, we use TDB databases to store various internal bits, and TDB originally is not a clustered database, so at some point, as we've learned, CDB was invented. And so an API was needed to actually hide away from the file server process which database backend is actually used, a clustered one, a non-clustered one, or whatever. So this is an API to abstract away the internal details and locking details. And so dbrep is an API that supports different backends, and one of them TDB, CDB. We also have, for example, a backend that does in-memory just read back trees, which is used a lot, I think, also. Yeah. Yeah, so for authentication, just skipping over this, this is madness last year, as I would say. This is really quite convoluted, spread all over the code. We have the so-called GenSec, generic security framework, that provides authentication, authorization, and data integrity, and it implements the authentication protocols, and it lives in a top-level directory auth. And then we have the low-level crypto routines, which do the NTLM-DS network on S channel. For other crypto, we also use, these days we use GNU-TLS, but we still have for some stuff, we still have our own crypto, our own low-level crypto. And for wrappers on top, the code that implement, for example, S-channel network on that lives in this directory. We have a whole subdirectory that provides the higher level authentication support for the SMBD file server. That is all deeply integrated then with GenSec, with a low-level crypto routine. So this is quite tricky. Then we have the actual Kerberos backend that's used in the file server for GenSec that lives in this directory. So yeah, getting this all sorted out in your head, that will probably take your time. So my recommendation would be, yeah, ignore authentication for the beginning. So now just mentioning briefly a few other important stuff that's there. We have an RPC server and RPC services. We have our own IDL compiler written in Perl that translates IDL files to source code stubs and the marshalling code. That's closely related to the RPC server and RPC services, but also used for other stuff, for marshalling data structures in NDR format. Then we have a so-called load parm subsystem and libraries, which is actually basically for processing our configuration, smbd.conf, but not only processing configuration file. We also support other configuration backends. For example, basically having it in a database, in a TDB database, the so-called registry TDB, registry config. And yeah, as I said before, we also provide local SAM with users in groups, PassDB and GroupDB, which live in the source3 subdirectory. All right, so next step is now from overview and high-level subsystem and library, get down and dirty and start looking into the code, and hopefully some of this that comes next year gives you, if you start looking into this, it gives you an idea how it gets started, how we set the ball rolling from the main process to actually do processing of SMB packets. For me, it took me some time going back and forth and all the structures and so forth. So hopefully for a starter, this is something that is useful. So really starting with a, oh, yeah, what's happened? I wanted to click on this, but that takes me to the next slide. So the main function in server.c, that's the one that's in the parent SMBD process, which opens the sockets, gets file descriptors, and we pass that file descriptors to our T event library. to get notified on this callback when there's any activity on this listening socket. Then we enter with SMBD parent loop, we enter the main event loop in the file server process in the parent. So whenever any connection comes in, that's going to get continued in the SMBD accept connection function, which basically then does an accept and fork. The parent then just goes on, it closes the accepted socket again and moves back to the main event library, accepting new connections. So after the fork, now from here on, we are in the child process. We're called SMB process, and now here allocate some core objects that we use in the file server to track global state and session and connection state and tree connect state. The first thing to do is we allocate a client object. We allocate a global. So we'll often use these variable names because we use those consistently across the code. So this scon variable, you will find this in a whole lot of places, is actually a struct SMBD server connection. And we allocate that's global state that we have in the process. And then we create an xcon object. We get that from this function that we pass the file descriptor internally. That again passes this file descriptor to our T event library, which will cause this function to be called whenever there's any activity on that file descriptor. Boom, and now we go back to the event library and wait for I/O on the file descriptor. When I/O comes in, that will be going through this function. That's not quite on the next slide. It comes afterwards. In between, we have another nice graphic which gives an overview of the objects we saw on the previous slide, and the way they are linked together and they are referencing each other. So the top top object is actually the struct SMBXSFR client, which the variable name often is just client, but this is the structure, which contains some basic client state. But the more interesting global structure is this one, the struct SMBD server connection, which, for example, contains a reference to our event context and the messaging context and a whole lot more. These are just two of the members in this structure. So we have then reference from the client state. We have a reference to the xcon connection, which we saw earlier, where it was allocated. There's typically only one, but with multi-channel, you can have more than just one. And then we have the SMB sessions also hanging off in the list from the client state. Typically, also, there's only one, but there can be more. And then the actual tree connects, so the connected shares. For SMB2, they're hanging off the sessions, but for SMB1, they're hanging off the client state. As I've mentioned in one of the first slides, this is a fallout of how SMB2 and SMB1 protocols are designed and work. In SMB2, tree connects are strictly tied to a session, and with SMB1, it's multiplexed. So continuing down to this structure, which is probably the most important structure that anyone working on a VFS object in the VFS will come across, and it's also passed around a lot in other internal functions, the so-called, just again, the variable name that you will see often, con, the struct connection struct. This is referenced by the compat member in the tree connect structure, and this is the one that actually gets passed around in most of the processing functions that do some real work to implement the file system semantics. And this is basically still more stuff that's related to the SMB frontend processing and holds references to the lower level file system stuff. Of course, we also have somewhere we store our file handles in a list, so one or more, if there are any, and those are referenced via a list from the scon global state. So remember, previous slide, smbd server connection handler is the function that gets called whenever there's any I/O in the forked child coming in. And suppose now we have an SMB2 connection and we get our first SMB2 packets and SMB2 negotiate protocol request. This first starts in, this is all clickable, at least here on my system, in slot3 smbd process.c. This is some interesting stuff. We get a callback data here, and this is getting the connection object from the callback data. We call an internal helper function for processing I/O and reading I/O for reading data from the socket. We receive the full packet and then kind of process the packet to pass and reference to the XCON structure. And in this special case of accepting a new connection, we call this function to process the negotiate protocol and negotiate protocol. And this is now where we actually move to the glory and very nicely structured SMB2 server code, where the main stuff here lives in smbd2.server, smbd2_server.c. We initialize some stuff. We free the old event FTE file descriptor event handler. That's the T-event abstraction that holds the state for handling I/O on the file descriptor, because we must remove, this was the previous handler and we want to set a new one. That's what we're doing in the next step. We set the new SMB2 connection handler. And then we call the request dispatch function to actually process the negotiate protocol request. So, and this is actually something, very core function for the SMB2 file server. This is the core function that dispatches just any SMB2 request. So after the negotiate protocol completes, skipping actually further processing of this request and sending a response. So we suppose the negotiate protocol completes successfully, and we establish the connection. And then any subsequent SMB2 requests will be handled by this function, SMB2 connection handler. Whenever there's I/O on the lower level file descriptor, we process this I/O. We we prepare a new SMB2 request object, and then, we call the SMB2 request dispatch function for the request. So, in the case of SMB2 create, the dispatch function is called SMB2 request process create. Similar for other SMB2 requests, you have process read, process write, and so forth. And these are basically the SMB2 front-end functions that parse the SMB2 packet. And in the case of the SMB2 create, we then call an ASIC function that's called create send. And create send is actually a big function. SMB2 implementation of the SMB2 create function is one of the, I think it's the biggest one in the whole code. It does a whole lot of stuff. I'm only mentioning some of it here. In SMB2, we have create context blobs. We process special SMB2 features like durable handles and create replay. We actually do the path name processing that we get from the client in the SMB2 create. This has to deal with a Windows case insensitive semantics and also with wildcards. And finally, we're called into VFS, into the VFS create file function. And that's basically where all the real fun happens. So create file. In Windows, in the Win32 API, there's a create file function. And it's similar to POSIX open in that it returns a file handle. but on Windows with its NTFS file system, you have additional semantics or different semantics compared to POSIX. You have sharing modes, read, write, and delete, a concept that doesn't really exist, at least in POSIX. You have some support for that in special Linux APIs, but typically POSIX doesn't know about that. It supports caching, so-called oplogs for SMB1 or leases for SMB2. Yeah, we have some NTFS behavioral differences for although delete and close is not covered, well, at least delete and close is a feature that we just don't really implement in that way in POSIX. You have different behavior for byte range locks and timestamps when you have write IO on a file. And of course, there's additional NTFS file system metadata that POSIX doesn't know about, like the Windows DOS attributes and named streams, for example. So the function SMB create file, as called by the SMB2 frontend code, calls into the loaded VFS module stack. And then every module that is configured and loaded by the file server implements this function is called in the configured order. And typically, this VFS create file function is only implemented by the so-called VFS default module. That is the default module in the file server that is always loaded, and it's often the only one. But at least it's always loaded, and it's the last one in the stack. And if previous modules in the stack didn't intercept the function call and don't pass on the request to the next module in the configured stack, then FARFS default would typically, and this is probably the case in 99.9% for this function file server configurations, if not 100 these days, and VFS default is the one to take this call. And this then calls create file default in this file, open.c in source3 smbd. And this is a wonder of a file with wonderful code that is quite tricky and complex, and which does implement all the NTFS semantics that I presented at the previous slide. So let's drill into it. We start at the top level. That doesn't really do too much interesting things in create file default. There's some stuff for quota support. A recent addition is SMB2 POSIX work in process extensions support in our code. There's not much happening at that function, which is basically then call another function create file Unix path. There we do some stuff to dealing with lists. Not going into details about that too. Here we don't have the time for that, I guess. Then we call open streams for delete to prevent deleting a file if any of its streams is open that doesn't allow deletion. So I'm dealing with streams and the special deletion semantics of NTFS. We have a special access check related to SACLs for auditing support, which is not really implemented in Samba. And so it goes on and on. For some stuff for the named, this is called the named stream support. If this is an open for named stream, we can basically recurse into the function just to open the base file. So this is still some high-level stuff, and in this function, that's where the big divide happens between processing opens for directories or files. So either we're going to call open directory or open file create. And if these functions complete, there's some post-processing, like setting additional extended attributes, allocating disk space if requested in the SMB2 request, some ECL stuff, setting requested ECL or inherited parent directory ECL. And now it gets more interesting. So open file create is a function that you may want to look at, because that implements some very core logic. It starts with some support for async create. So create is one of the functions that we support processing asynchronously. After that, it calls the low-level open routine, so a function open file, and that is the one that sooner or later actually calls into the VFS with the open function, or not anymore. This just got changed last week. We're now calling the VFS open add function. And subsequently, it deals with any errors from the open functions that may suggest a retry to process asynchronously, and calls the function setup poll open or schedule async open to cope with them. And then it goes on to really implement all the interesting NTFS stuff. So we have this function get share mode log that returns a log object, and this fetches the record from the logging TDB database. So what is logging TDB? That's our central store for all the file handle information. Internally, here we use the DB Web API as mentioned before, but that's the higher level function that's used here in the open file integrate code to get a handle for an object that presents as a structure the internal contents of the low level record. And when we have that and handle on that structure, we go on to processing that and then checking for delete and close semantics. We implement sharing mode and oplog leases with these functions, handle share mode lease and set share mode. And afterwards, we do some, we continue processing NTFS metadata for Windows attributes. Those mode is the function to read those attributes from our file system, and file set those mode is the function to set it. And then it goes on a little bit more. But this is one key point here, this function to get the record, and the functions that implement the sharing mode and upload key stuff. This is pretty very stuff that you sooner or later take a look at and get an understanding of what it does. So a few more words on logging TDB. So how does it look like? Inside in the record, we have one record per file that contains the open file handle information. In the record, I hope this is still correct for current master. Volker is currently reworking all this, but I think this is how it's currently still working in master. We have a fixed size header with struct share mode data, which contains some global state for the file, and then we have the actual struct share mode entry array, which contain information about the open file handles per file. And this stuff looks like this. So this is the global struct per file, where we, for example, store the name and the share path of the share. We have the share mode flags, and this is what Ingo mentioned in his presentation. This is the most restrictive set of the sharing flags, for example, and the combined access of all the file handles on the file. And we also have then an array here of pending deletes on the file, and some timestamp stuff to implement the Windows NTFS timestamp behavior, and so on. And on the next slide, we see the structure that actually the share mode entry, and this is per file handle, where, for example, then we store the access mask and the sharing mode in these two members, and of course some other stuff. So the reference section.
I'm sorry, so we are at the end of the time.
I know, and I'm at the end of my presentation.
Oh, that's great.
Q&A. Okay, so let me try to get back to see if there are any questions, or there's probably no time left, right? So, but I think it doesn't look like if there are any questions. Oh, my cursor was not visible. Dread. So Jeremy is asking how much of this changes with the add changes. Well, one thing is already changed in the slides. We're calling open add and not add. Yeah. But basically, all that is still applies, even with the ongoing EFS modernization effort, where we are where we're basically replacing any POSIX file system calls that are not add variants with add variants. So we're using open add instead of open, fstat add instead of stat, and so forth. Some of these calls are still missing, but this is how the EFS interface is going to look in the future. Yeah. Okay, I guess that's it, right?
Thank you very
Thanks.
much.
Anybody who listened up to this point and didn't fall asleep. Bye.